So thank you so much for having me. How is it going on with your digestion? You're alive? Yeah, okay. Let's see how it goes. You're not, you don't respond. Okay, fine. So, yes, as Jen was saying, these are the universities I come from, and then I went to Prague with the Marie Curie, and now I'm at the Czech Technical University. These are my angels. I used to call them my angels because nothing I can do without them. These are my students, and today we look at what's catching your eye, which is very easy. If I ask you why you're interested in that point, easy, right? Intuitively easy. But then if I ask you, okay, but why you're really looking there, it's not easy to understand, right? To really define why we look in certain places and not in others. It's not that easy. And I do it through the lenses of event-driven and neuromorphic computing. Okay, ready? Shall we? There we go. Now, this is the dream of everyone, right? You're taking your call, right? And then in the meantime, there is a robot that is preparing a cup of coffee for you whilst it's cleaning. Is it happening? Guys?
No.
Thank you. Otherwise, it's going to be so boring for me having a monologue, okay? So let's discuss together. It's not happening, right? Although media wants us to believe that it's happening, it is not. For many, many reasons, right? So some of the reasons, they do not move in unconstrained environments, right? You can train as much as you want, but what if you switch the environment? Well, then you need to relearn in a new environment how to move, right? Not easy. The other two problems, which if you talk with roboticists, they're like, no, actually the power consumption is not a problem because the engines are already using lots of power. It's not true, because at some point the robot will need to listen, see, move around, and so on and so forth, right? So the power consumption at some point, when the robot will be really complex, it will be a problem. Same thing with the latency. One of the major issues when you work in robotics is that you talk to a robot and the robot takes a second to respond to you. And then humans, what's the first thing that they do? We get bored and we don't interact with the robot anymore. Okay, so this is a real problem. But let's focus 1 second on these guys, okay? So the cat is playing nicely, beautiful, love them. And the dog knows that if he's giving it a paw, he's receiving something, right? It's so easy for them. Do we have in robotics something that easy?
No.
Ah, thank you so much. Yeah, you got what you need to do. Thank you so much. Now, in this moment, I am moving. I'm thinking what I have to tell you. I'm also thinking, oh my God, it's going to be so, depressing for them after just having lunch. It's going to be super difficult to make them attentive, and I'm thinking of what to say next, and so on and so forth. All of this using 20 watts, right? So I don't have to give you many more motivation why I look at nature, right? This is inherently interesting. Let's go down to the problem. How do we define attention? As I said before, if I ask you why you're attentive to a certain point, you can say it intuitively, but how do you define it exactly? Most importantly, here, it's doing a lot of things, the cat is about to burn to hell, right? So somehow, I need to tell the robot, forget about everything else, now this is the most important thing to do, right? Okay. Now, I'm gonna play this video twice, and then we discussed about it. Okay? Just look at it. Is it doing what I want? Is it doing what I want? Ah, no. But it's not based on internet, so I don't understand. Let me get out. What's going on? You don't see it, but I have this with me. Let's see if I can get out. Oh, wow. I don't know. I don't know what's happening. It's completely frozen. And even if I press ask, nothing is happening.
Maybe we started questions. Are you on Mac or PC?
Sorry?
It's Macintosh or?
It's a Mac. Maybe let's do this. Let's see if doing anything.
I'm not choose to just crash it on the chat.
No, but it's not even, it's doing nothing. Completely crashed. Let me see if I can quit some of the other things. I don't know, it never happened.
If you need the key, you can switch presentation to the other computer.
But it's impossible. How I don't know how to give you the presentation is more than 2 giga. We're gonna lose the day. I don't know.
Just restart the whole computer.
See. Yeah, but weird. That's really the first time ever.
That means 2 really good people.
No, but it's not that the problem. It's the first time that I get this frozen because of the... No, but it's not a connection problem. I mean, I can...
Force reboot.
Yeah, but it's not super good, but fine. Yeah.
You might need to restart, right?
I'm trying, but I'm forcing reboot, which I don't like it that much, but it's not even doing it. It's not doing anything at all.
I hope you didn't lose any unsaved work.
Sorry?
I hope you didn't lose any unsaved work.
I don't know. We will discover it later, but... Maybe it's too hot. I don't know.
It's a good point.
Hmm?
In the meantime, I take the opportunity to tell you that this seminar series is brought to you by, with the help of IDEX, Academy, Needs, Networks, Information and Digital Science. And we try to have this kind of seminar once a month over the academic year, between October and July, or June or July. And we very welcome your own suggestions. If you are in touch with some collaborators, some potential speakers, if you would like to invite someone over, like to start a collaboration, you can send us some, send us names, and we will study if this is possible. And we are now preparing the next season from October 26th. So if you have any idea, you're welcome to send them.
Okay. Okay, let's see how it goes. Thank you, Jen. Okay. Let's get back to me. Let's look at the video. Should play twice, yeah. Okay, what have you seen?
I've seen something.
What have you seen?
See a guy answering a phone.
Yeah, something else? Let's go. Let's go. Oh. What have you seen?
First thing we can see type on a keyboard and
Yeah.
in front of the screen that was a bit inclined, and on the far they were Dell computer, and there was something also, I don't know what it was, in the
Okay,
glass.
okay, okay. Something else? Give it to me. It seems too obvious, right? It's beautiful because when I ask this question, it tells me much more of the people than... So what is this? Something happened again, whatever. Anyway, these are 2 completely different people. Now I see it. Okay, now, you missed it. Why? Why?
Because everything else
Everything is valid, yes, but I want a response from you.
I didn't,
Oh! What?
I didn't look at the face.
You didn't look at the face? Good hint, hint, hint. There is a hint here.
I don't know. I would say maybe we are biased by his.
Easier, easier. Too complex. Attention. Attention. We don't look at every detail in the scene. We just move our eyes around and we get what is informative from the scene. We do not retrieve any specific detail in the scenario. So I just proved to you that frame-based skimmers are wrong, or at least they don't mimic what we do, okay? Because if we were acquiring for frame-based, we would have done the subtraction, right? We don't. We move our eyes around and we just get regions of interest around and we get, okay, what is telling me? Indeed, all of you, with the lots of details from you, just told me someone was typing and then responded to the phone, right? Good, your brain is working fine. Good to know. What is this? Come on, what is this? Nobody? A machine from the gym. Ah, the subjects there would have loved that, but it's an eye tracker. Okay, you put your chin here, forehead, and here you're looking at the eyes. Okay, so imagine doing it for science back there. So this is 1967 as Alfred Jarbus, and he was looking at how we move our eyes around depending on attention, okay? With a task, in free viewing, whatever, doesn't care. Now, we have the image which comes from a very old book, you will excuse me, and this is the scan path, okay? So the recording of where the eyes are moving around, okay? Now, what is going on here? There is no response that it will be considered stupid, I promise you, because I do stupid things. So what is happening there in the first one? We are moving our eyes, and where are we looking?
There are 3 people.
Sorry?
There are 3 people.
Yeah, and we are looking at what?
And 3 of them. One is trying to leave and one is coming.
Uh-huh, interesting, yeah. Anything else?
Especially faces.
Faces, okay. Anything else? It's, yeah?
The control of the scene. I don't know.
Okay, so it's way more, stop being a scientist for a second, thank you so much, and being human, okay? If you are in your apartment, okay, and then you hear some noise outside, what do you do?
Look out the window.
There we go. You look at the window and it's, oh, what's going on, right? And you stay there, right? So it's much more human related. You got it. It's trying to understand what is the social interaction here, okay? Are they fighting? Are they discussing? What's going on? Let me understand. Should I enter the room or maybe, oh no, okay, and I leave it, okay? What we do here, you know, you said faces, recognition, triangulation. Here, we look at the foliage and then there is a big piece of contrast, which is a bear. Then we get here and we probably run, okay? So, at the end of 10 years, Jarbus came out saying, look, I have no idea how to describe attention, how to tell you why we look in certain places and why not. Of course, I can retrieve some sort of patterns, but we extract the most informative information. This is what I got after 10 years. Okay, let's go on, which wasn't promising at the start of my PhD, but fine. Now, what we have here is the scan path. So the scan path from humans, okay? This is where humans look at, and this is a saliency map. A saliency map is trying to tell you where we might look at, because there might be something that is interesting. You can see already that this saliency map it's wrong, right? Because we have a big information here that the humans don't care. Why? Is what I was trying to tell you before, because we are biased, way biased. So when we go to the beach, we look at the horizon most of the time, okay? Even though there is a big contrast there. So in 1998, a group of people, which are my mentors, E.T. Loren, Christoph Koch, and Ernest Niebuhr, tried to come out with an idea, with a model that was a bottom-up model, to give us a saliency map, okay, for robots, for agents, to understand where we could look in certain places and what not, okay? So this is very easy. We have intensity, color, and orientation as channels of information, as fully bottom-up. So what we are doing here is just feature extraction, okay? And then we merge them together to get a saliency map of the scene. Now, cool, very cool, but feature extraction is not enough, right? We will not go anywhere with only feature extraction, right? Then the question is, how do we perceive items around us? How do I know that this is a thingy, okay? And I should look here because this is a thingy, and then the recognition on top of it will tell me this is a mobile phone, okay? But there is a step before the recognition, right? That is telling us, look there, because there you might recognize something interesting. Is a step before. Well, Gestalt, okay? So in 1950s, so same time of Yarbus, lots of scientists, this comes mainly from psychology and philosophy. These are Gestalt principles to rule vision, okay? So to try to understand how we perceptually understand the visual cues, okay? Let's start from the first one. What is this? What is this? What is this? It's not true, right? It's so easy, but it's not true. These are 3 out or 2/3 of the circles. These are just lines put together, right? And these are dots put together, right? Why? Because as human beings, we are used to label. We need to label. We need to label things because then we are not scared anymore and we understand the scene. So what do we do with it? We try to perceptually group the information together, saying, oh, that might be, I've seen it, okay? But to be precise, this is not a square. Someone should have said this is 1, 2, 3, 4, 5, 6, 7 lines, which some of them are corners next to each other, okay? Let's go on. We group for similarity. So if I ask you, give me 2 groups of this, you will do circle by circle and triangle with triangle, right? Fine. Same thing for proximity. If I ask you to group it, it would be so weird for you to group something like this, right? You will group for proximity. And this is instinctive, right? And this is easy, figure ground organization, so you understand that I am the foreground and this is the background, okay? The distinction between the two. So these are the rules that in 1950s, the Gestalt and Gestaltism tried to, explain what is the first thing that we do with the visual cues. Well, in 2000, Zhu et al. Found some interesting cells, okay?
Excuse me.
Yeah?
A second.
Yeah? What do you need?
I think we have a problem with results.
Perfect. Okay, you hear me? You hear me fine? Okay, fine. Now, let's look here. This is the cell. This is different trials of the same cells in time. And then we have, you can see the different background, color of the background. In the upper case, the object is on the left. Bottom case, to the right. What is the difference between these two? Come on. 3, 2, 1. There we go. Density of the activity. Yes. So somehow the cell knows that the object is on the left, right? But regardless the color, how? how a single cell knows that the object is on the other side, okay? Because we take very much for granted everything we can do with our eyes, but it's a little step one after another one. Let's try to look at this. In V1, in the primary visual cortex, not only there, whatever, you will excuse me, we have Gabor filters. Gabor filters are used to get the orientation of the edges, right? So we have one side that is excitatory and one side that is inhibitory, right? So in this case, we are looking only at one edge and the orientation of this edge. But in the brain, we have hypercolumns and columns next to each other with bunch of the same cells of different orientations stacked one next to each other. Then, if you have this cell, and this cell, you can see that the grouping cell complexively knows that there is something inside because all of the excitatory parts is inside. Therefore, the grouping cell knows that there might be something, an object, close contours, okay? Same problem of the square, okay? There might be a region where we should look and pay attention. It's a step before of the recognition. So this was the start of my PhD. Chiara presented me this paper from Russell et al. And Ralph Etienne Cummings. And she was like, okay, this is your model. Not true, sorry. This is your model. And let's try to make ICAP attentive. So the model is the same one of E.T. Koch and Ernest Niebuhr, same one. What it's different is this two part, okay? So in this case, we convolve with the different orientation of the von Mises filter. I'm gonna tell you what is a von Mises filter. And then torch sum, okay? We just squash things together to see. Now, the von Mises filter is this filter here, and it's trying to replicate the idea that you have this grouping around the close contours, right? You have this curve filter, and it's kind of like resembling that close contours. And then you will have different orientations, and you close the area. Okay, let's go on. Now, question I asked myself, and everyone asks me, is it fancy bio-inspiration? Let's see. At the end of the talk, I will ask you again, and you will tell me if I convinced you or not on my work. So, this is ICAB. These are the event-based cameras, which I will not explain at all today. I think everyone is okay with it. And then the channels that I wanted to have was depth, motion, and intensity. Intensity because it comes free from the camera. Easy. Then I wanted to have depth because the robot, if it needs to interact with things, needs to know where they are, right? And motion. Motion is inherently interesting. Motion is one of the most interesting things on the planet after faces. Faces are incredibly interesting for us, of course. This is what I managed to do through my PhD. So we have the channels that I promised at the start, motion, depth, and intensity. So you can see that you have two models for the intensity. We will talk about it later. And these two are fed into the proto-object. The motion is not fed into the proto-object. Why? Is there anyone that wants to try to respond? Why I don't care to detect if it's an object or not for the motion channel? Try. Say random things. It's okay, I don't care. Try. Okay, let me try. I need this. Oh, okay. Oh God, it's too hot here, guys. Like I can't wait to go back in Prague. So if I do this, there we go. Did you care to recognize that this was a bottle?
No.
Right, because it's moving very fast, right? So you were just like, what the fuck is going on? You know?
Okay, I knew
I know. But you know, there's always with 1% of not trusting the others, which I agree. Which I agree.
I mean, natural instinct.
Yeah. Anyway, motion is inherently interesting, right? We do not care to see what it's coming towards us if it's coming so fast, okay? We just need to either catch it or run away. Perfect. So this is what I have done, okay? In this case, you have the intensity channel. So you have the robot that it's looking at the object, you have the events and the saliency map. And now I will put another object. You can see that I'm disregarding a line. A line is not close contours, so it's not an object for me and for the model. And then I interrupt with a paddle. Now let's move 1 second here. This is the depth. So this has been a bloodbath between me and Shuman Ghosh, which was my first master's student. So what you can see here we have the stereo cameras from iCub. So I take the rectified stereo events, and then we do the disparity map. How we do the disparity map? With lots of praying and the cooperative stereo matching model of Jörg Conrad. So basically we are trying to solve the uniqueness of one point projected into the two planes, left and right. Whatever, long story short, gives us the disparity map. So the higher the disparity, the closer the object is to us, right? Because the higher the disparity, the closer the depth. So what does it mean? If I convolve the von Mises filter on the disparity map, it means that objects that are closer to the robot will have a higher saliency map, right? So somehow I gave a task to the model, right? It's not bottom-up anymore. I'm kind of like enforcing from the structure of how I created a model to look at objects that are close to the robot. For what reason? Here you have the normal attention, here you have the depth attention. So let's look at the video. For this problem, attention is moving from here to here, and here is stable on the closest object. Why? Because imagine the robot, you know? You need to take a choice, and the choice is the closest object, period. Here we have the motion channel. It's based on the Reichard model. Maybe we will talk about it later, but it's based on a very simple model of elementary motion detector. Fine, I don't have it. Do we have a, no, right? It's okay, whatever. Anyway, you have two units, one next to each other, and then a delay between the two, connected to the same neuron, okay? So if something is triggering this before this one, this is the direction of motion. Easy. So you have left to right, right to left, top to bottom, and bottom to top neurons. What I've done here is my obsession with the retina and the log polar retina. So we do not see clearly everywhere. We will explain it a little bit better later. Maybe it's the time for the question. So I just said that we do not see everywhere clearly, us as humans, right? Do you know why?
Too much information for our brain.
Yeah, that's the problem. But how we have solved it through the retina?
We see well in front of us, and
Bravo.
for the side we don't see very well.
Perfect. We have the fovea, which is the center of our retina, is the only part that is highly resoluted, with which we see things, okay? So now I know that the phone is here. I'm gonna steal it at some point, but I know that the phone is here, right? But to see it clearly, I need to move my eyes there, right? And why? For what he said. Because the optic nerve is a pipe. It's not magic. It's a pipe. So if you want to push data, there is a throughput at some point, okay? So we need to understand what we want to send. And this is determined by attention. And the fact that we have the fovea and we foveate around, that's part of the attention mechanism. Now, The question is, how much in percentage do you think is big the fovea in the retina? Give me some percentages. How much do you think is big? 10%. 10%, okay. Someone else? 1%. 1%. Imagine how many things we mix up. Okay, so trust less yourself and what you see, okay? Because we don't see clearly. We have 1% of our retina that sees clearly. Okay, let's go on. Results, okay? I have many things that I want to tell you. Maybe I'm gonna go very, very quickly on this. Here we compare it against the RGB model. Fine, we are better because we are more localized, because we start with events. Same thing here. You can see that the structural similarity is higher in comparison to the frame-based one, because look at the 3D fixations and look at our saliency map in comparison with the RGB one, which is the one, what I was telling you this morning, right? You have a center bias here, you have a dense information. Look at how precise we are, right? You lose this, which is actually nice. Same things here. These are the metrics that I was saying, the MIT metrics. With some of them you had it too, and so on and so forth. Let's not stay too much here. I want to tell you other things. And this is Paolo. Paolo is my PhD student, and we are trying to look at how to use the fact that we have this eccentric retina, okay? It's called the eccentricity, because the receptive fields becomes bigger and bigger going in this direction from the fovea to the periphery, and it's called eccentricity, the distance from the center. So we are trying to, this is a representation of the log polar fair representation of the retina, kind of fair representation. And here you can see that the stimulus activates this different part of the retina depending on the speed. Is it a GIF? No, it's a video. Let me play it again, okay? So here the stimulus is fast, and here is very slow, very, very, very slow. Look at what is activating here. Just the center is correct. Because when we need to recognize things, we move it in the center and we don't look at very fast things. The periphery is attentive to fast things, because for that reason she could move, right? Because everything that is entering the visual field needs to be taken into consideration very fast, okay? So the periphery is getting fast things, so translated a very fast tau. And in the center, we have an elongated tau because we need to recognize things, okay? Fine, together with Alexander Adijanov, we have a library that is starting from classical RGB cameras and is trying to give you all of the layers of the retina. I'm quite obsessed about the retina, you will see it even later. Fine, let's go on. Now, another question that I asked myself is, okay, but when do we get to segment somehow the scene, right? Wrong question, Giulia. We don't segment at all, but we rather continue with the idea of attention, and we continue with the idea of saliency, because, for example, like we are so biased by frame-based cameras that we think that we segment things around, people around. Is not true, right? When, for example, we need to recognize things around, I don't need to show you everything of this object. I can just show you this part and you will tell me it's a bottle, okay? We don't need to segment the entire object first, because we don't see it all most of the time, unless it's very far, far away, because we don't have the resolution in all the retina. And second, because we don't need it. We rather segment for motion, okay? So here we just added a feedback from the grouping to the border ownership, and we tried to reinforce the idea of saliency. What is very cool here is look at the response of the frame-based and the event-based grouping compared to the RGB input that we had. You can see that the frame-based look for the one that is very bright, and the event-based look for the one that is very dark because of the contrast, okay? Let's go on. Now, let's go back to the main point. So at some point I started doing the similar model so much that I started benchmarking against myself. So I told you at some point that the intensity channel has been made on a classical GPU, but it has a new version, and the new version we published it later on Spinnaker, entirely on Spinnaker. So this is just to show you that this is running on a GPU with 100 milliseconds. This is running on a GPU with 170 milliseconds. Look at this, right? 16 milliseconds, and we have a very good saliency map to work with. Same thing here for the motion, 4 milliseconds. It's basically unbeatable, okay? So already here we see the power of using these architectures, but you need to be smart in building these architectures. Okay, problem. We all know that the bigger the model, the more Spinnaker boards you will use. This is another paper that we tried to show and we tried to present with Luca Paris from Manchester, where basically we use the attention and then we put the winner take all on the scales. Of course, we have a pyramid of scales to be invariant to the size, and we output a precise region of interest against the region of interest deep learned by prophecy, and we are 15 times faster and reasonably comparable with the accuracy. And this is Mazdak. I feel some of you knows Mazdak. So Mazdak and he contacted me the first time after one of my talk, and since then we never stopped collaborating. So he's finishing the PhD and I will cry for at least 2 months. So don't talk to me when he will finish the PhD, because I will be very upset. So here what we have done is the coastline detection. And I think it's your data, right? Or exactly. So we had this data, and then we started trying to understand how to do coastline and shoreline monitoring with SNN. And then he was telling me, oh, let's use your attention model. And I was like, nah, it's not gonna work, because the attention model is working for close contours, and the shoreline has this shape, right? But why not using just von Mises filter on their own? The shape is that one, right? We just put them one after another one in vertical lines. And this is what we have done, okay? So here you can see the results. Yes, we have different intersection over union thresholds. And depending on the threshold that we use, we have a different accuracy, and depending on the latency to acquire the events in the bin of events fed into the Spinnaker. So let's say this, it's kind of like a reasonable idea that for 20 milliseconds, which is the lowest latency, we still have reasonable accuracy, and we have 0.3 milliwatts, right? It's stupid. And still, yeah, I want to show you, we are able to detect it. So look here. You have the ground truth here, our bounding box, and then the section over union. But then we were like, okay, we need to prove that it's working only for this and not for fuzzy shape. And then we tried to prove that too. And then we were saying, okay, but what if, no, this was Pierre, was like, I don't believe you guys, let's augment the data set. And then we augmented it, and you can see that it's working only for the shoreline, okay? And then I was talking with Ernest Niebuhr, and he told me, oh guys, why you just do it for this? You could actually use it for streets, right? Same thing. Okay, then I told Mazdak we have a new project, and he's kind enough that he followed me on this nightmare. And we started working on the pinball, okay? So the question here is, can a spike neural network play pinball? Apparently, yes. And it can do it way better than my students, okay? So this is my students, and somewhere there is also Mazdak. And this is the model, okay? So the model is way better in hit rate, miss rate, successful hits, and so on and so forth, okay? So this, what you see here is the camera looking at the pinball and the SNN flipping, deciding where and when to flip, okay? And this is our power consumption, okay? Let me know if you can do better. Yes, and this is our accuracy depending on the receptive field size. Okay, now, I gave you a little bit of my word for the visual attention. Let's move towards the retina. I told you that I am obsessed with the retina because, I mean, it's not that I don't like deep learning, but I don't, yeah, I don't like it. Give me one sec. Because we are way more complex and elegant than just feeding something to, you know, something that we don't even know how it works. That's why I was telling you these things this morning. So this is the retina, okay? In the retina we have different cells. All of them do beautiful things. But I wanted to fixate on the amacrine cells for now. The amacrine cells are horizontal. So we have vertical cells, which is bipolar and ganglion, and then the horizontal and amacrine, okay? Are horizontal because they are spatiotemporally integrating from a wider area, okay? Now, maybe, yeah, let me tell you this. So what the amacrine cells do, which I think will be useful for you, is trying to look in an area. No, let's start from here. I have a camera here, okay, and even-based cameras. What happens if I move the even-based cameras? What happens?
We get some events because the camera is moving. And
We get it everywhere, right? Yeah. Now, if I move the camera, and in the meantime, I move my hands in front of it, okay? What do we have? Events from the movement of the camera and how do we distinguish the two things?
You could perform a prediction of the action of moving the camera and update an internal model, and you perform a subtraction and just see the external environment.
Yeah, but you need to go to the cortex to do that. I want you to do it here in the retina.
maybe the depth difference?
The depth is in the LGN. I want you to do it in the retina. That's why I loved that you didn't use the IMU. In the retina, we do not even have proprioception. We do not even have the IMU signal. So we do not know where the eye is moving. So how does it solve it? Easy way. You have a filtering there. Guess what? Difference of Gaussian. And then what you look there is the distinction between the movement in the center and the movement in the surrounding, okay? So if everything is in motion, the center and the surrounding, that's coherent motion. So probably it's the camera that it's moving, okay? If there is something instead that is moving in the center, so there is lots of movement there, the suppression part from the surrounding, it's not that strong to suppress everything, okay? And this is the outcome. Look. Okay. Now, look here. 85%. I dropped the number of events of the 85%. This is still to prove you that the optic flow is a pipe. We have a throughput. And this is how the retina is working on this. Okay? This is another mechanism to drop the number of events to put into the pipeline. Nice. I have, of course, done a comparison with the EVMO. This is a data set, so this is the ground truth, and this is our response from the model. Then this is the full pipeline, okay? So here you have the events. Then you have the SOMS, so this model here that is just giving you what is in motion. So it's distinguished, it's not ego motion. It's distinguishing what is in motion from what is static from the scene, okay? Ego motion is more complex. Then from there, you put attention on top of it to understand if there are some close regions that I should pay attention to. I take the point and I give it to the control for the pan and tilt, okay? And then what happens is that the point is here, I want to look there. And I control and I give the pan and tilt to go there, okay? And I foveate there. Now we have the foveation here, but then here there is one of the most important things. These movements here, specifically this one, is the most important thing. Why? I told you that we look in a certain area, the distinction between the center and the surround, right? So I'm looking at things in locality. So how does the camera needs to move to make this model work? It needs to jitter. Okay? That's why I think it would be useful for you, because the robot will move like this. But the point is, now, when we fixate around, we do the saccade, so we do this ballistic big motion, and then we fixate on a point, right? And in that moment, our eyes are still, right? Are still? No. The eyes are never still, because if they were still, following the fact that we have event-based cameras in our eyes, we would see nothing. So we need to constantly move, right? So this is what our eyes are doing. Ta-da-da-da-da, poop, ta-da-da-da-da, poop, ta-da-da-da-da, and we continue. We just don't perceive it. But when we fixate, we continuously move. And we move like this, because if we would move around, we would not understand anything, right? So we need a little bit of jitter to collect the data, understand the situation, understand the scene, and then we can make a decision to move somewhere else, right? So this model would not work if you move the camera around. Indeed, when we perform a saccade, do we process information when we perform a saccade? You can get it. I told you, basically.
No, because it's motion.
There we go. We do not process information whilst we move. So if I'm moving from you to you, in this jump, we don't process information, which is called saccadic suppression. Okay? Now, 2025 Nature paper is disproving this a little bit. There might be a 5% of the information that it's processed, but it's a teeny tiny, okay? Because otherwise everything will be blurred. Doesn't make any sense, okay? Therefore, this is the proof of embodiment. Why? Do you know what embodiment means, guys? No. Perfect. Thank you for saying no. Okay. So embodiment means that you are able to perceive the table and perceive the word because of the way your hands are created, okay? So the body is experiencing the word in a specific way. Therefore, the algorithm that we have in our neural network, it's depending on the shape of the body, right? For example, if I touch you here and here, you will feel the difference, right? If you do the same thing on your back, you will not feel the difference because we have a different distribution of sensors. So this means that if I take your brain, I detach the brain, and I put it inside a crocodile, it's not gonna work, right? Because the body of the crocodile is completely different. So it's a co-design of the body and the brain, okay? That's why it's embodied. And for embodiment, to have this model running, we need to move in a specific way. We need to process the information in a specific way. Nothing will work if you take out one of these pieces, okay? So sure, whatever, another benchmark. Now I want to show you how it's working. You see? It's seeing the static scene, it's seeing what is a motion, and it's foveating where there is the only object in motion. Okay? So, who tells me which kind of learning there is there? Ideas? Ideas? Which kind of learning? Active learning? Something else? There is not a single line of learning there. I messed up with you guys. Because we don't need it, okay? Because we need to use learning where is needed, not everywhere, okay? Learning is abused nowadays. The retina solves this problem. These are my cats. The retina solves this problem without using the learning there, okay? Nowadays, we take a bunch of data, boop. No, we can still do stuff without. And this is working indoor, outdoor, everywhere, in the desert, in my room, everywhere, right? Which is the power of it. When you start doing things that are more complex, like recognition, then you need learning. But you need it there, not here. Look at it. I'm moving in my kitchen at different distances. Do you see a problem with it? It's working fine, right? Imagine if I would have had to train it, how many days I would have spent, and then I would have, you know, move in different position and collect lots of data. I did nothing of it, okay? This is running on my Mac in 120 milliseconds and on the spec. There we go. So this is running entirely on the spec. So in the previous case, we take the events from the spec and then we run it on my computer, on my Mac. In this case, it's entirely on the spec with the trick that we were talking about, I think with you, no, with you, I don't remember, the frequency trick to have the leak, integrate, and fire. Otherwise, my life is done without leak, integrate, and fire. Of course, it's worse. It's worse? Yes, we know it's worse, but it's running on a spec pipeline. I'm doing it with my best buddies there, and what we want to prove here is multi-neuromorphic platforms working together. Spinnaker for the control and spec for the vision pipeline. And this is running at 1 watt power consumption. This is how much we use for the frequency, just to whatever. Now, let me provoke you a little bit. What's the time? Geez, I should finish, right? I should finish. Yeah. I'm gonna run. There is just one thing that I want to tell you, the last thing. I'm sorry, guys. So here we have the OMS map, okay? And here we have the saliency. Look at the difference between a time window of 10 milliseconds and a time window of 124 milliseconds. What's the difference of the saliency? The saliency map is way better if you wait a little bit and you understand what's going on in the scene, right? Here you can see that all of these are saccades. Imagining how many places wrong we would have gone with our eyes. Look here, we wait 1 second, we understand the scene, and we look to a point that makes sense, right? Therefore, my provocation, I don't know how to say it in English, is can we please stop to try to go as fast as we can with event-based cameras, because the world doesn't go that fast, okay? Unless you need to detect subatomical movements of cells, nothing is moving so fast that you require 1 millisecond update, okay? Not nothing, there might be something, okay? Fine, but it's so rare. If you need to detect a person talking, moving, walking, you don't need to go that fast. So just wait a little bit and spatiotemporally integrate the information in order to take a decision afterwards, which is what we do with our eyes. Our photoreceptors integrate for 20 milliseconds. 20. Can you imagine publishing a paper and saying that every 20 milliseconds? Now we would be killed, right? But this is what the retina is doing. We wait for 20 milliseconds for that. So my provocation is this one. Now, let's go on very fast. We attached on top of the OMS also the direction of motion. So now we distinguish between what is in motion and what is in the background, and we also know where is moving, and this is job done with Jamie and Ricardo. Then this is the last thing that I want to tell you guys. It will take 5 minutes. I'm super sorry, forgive me. Now, what I've told you is that we are forced to move around with our eyes. So we are forced to explore the scene, right? Now, I'm trying to revolutionize, quotes, 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 computer vision. Why? What is this? It's a baby and it's playing around with a toy, right? So it has a toy in the hand, it's moving the toy and it's looking at it, right? Why is it moving the toy in the hands?
Curious. It's curious about.
Yeah, but the curiosity, what purpose is giving? Understand, but what?
The shape,
Is
3D.
yeah, it's solving also occlusion, right? It's solving occlusion. It doesn't know it. She doesn't know it. The baby doesn't know, but it's solving the occlusion. It's in my hand. If I move like this, I perceive that my hand moved, and the object is in motion, so I understand that it's a 3D thing that is moving, and so on and so forth. So he or she or whatever the baby is experiencing the object, okay? Stay there 1 second. Now, different study, 2 groups of people. One group was able to explore the object. The other group was exploring the object based on the explorations of the others, okay? And then at the end, they have been shown the objects and they have been asked, do you recognize this object, yes or no? The active ones recognized way more objects, okay? So there is then a meaning. There is something ingrained in the experience that we have with objects. One is here. We are so biased by frame-based cameras that we used to think that we experience the world in frames, which is not true. We move our eyes on the object. And the movement, the saccade that I do over this bottle is completely different from the saccades that I will do over this PC, right? So what if the sequence of the motions that I do with my eyes, together with what I see in the fovea, together they classify the object? It will be a different sequence. So I am not learning the object because of the image. I am learning the object because of my specific experience on the object, okay? So this means that if you show me the object in a completely different environment, now I recognize it, right? Because it's encoded in me, right? Okay, this is what I'm trying to do, and it's part of what Dana Ballard was trying to do before. We don't have Dana Ballard with us anymore, unfortunately. But the idea is that we do not store everything in our brain. We do not have 3D models of objects. We don't have internal models of objects. We rather have a sequence of our experience on the object. Okay? And this is the idea that I had for my Marie Curie and what I started to do. And is what Sharka is trying to do using either vector symbolic algebra or contrastive learning through time. So it's trying to push together things that are close to each other temporally and similarly in terms of vision. And vector symbolic algebra, it's something that is coming from Waterloo, which is basically using the vectors to represent the features okay, that we extract, which would be the sensory information and the position, the saccade. Okay, so this is Ola, and this is my bachelor student that just graduated with honors, because we also published together. We started together just doing object recognition, number recognition with Spinnaker 3. So we're looking at the object, and then we recognize the object, and then we moved towards sign language recognition. So you can see that we have here the attention that is telling us where to look at through the saliency, and we recognize the sign language. And this is done like this because, I mean, potentially we could have the neuromorphic chip running on glasses, right? It's very small, and it could be turned on for 3 months, you know, without any charge. Because you can see these are two different data sets, 0.7 and 0.5 milliwatts of power consumption, and this is our accuracy, which is actually nice. Okay, we are towards the end. This is Lukasz. Lukasz just graduated, and he joined the dark side of the companies. So what he has done here is event-based tracking and eye blinking. I want them together because most of the time you just have them separately, whilst actually is the combination of the two that for automotive could tell you if someone is going to sleep or is falling asleep or is drowsiness detection and so on and so forth. Then there is Rai. Rai came from Brazil to work with me. We won together a fellowship for her to come with me, and then she's working on audio. So she's trying to do keyword spotting on FPGA. We just have the FPGA in our place. And what we want to do is to modulate the visual attention with keyword cues, right? So you have the visual attention, and then I tell you, look at the object on the left. He understands the left, and he moves. So the bumps of the saliency will start increasing on the left side, okay? There we go. So this is just vision, right? But this is not enough, right? We have touch, we have locomotion, we have skin, proprioception, we have lots of things. So this is just my recent publication with lots of beautiful people, where we think that the best for neuromorphic would be in the combination of neuromorphic and soft robotics, because soft robotics needs to handle different time scales in a very precise manner. So you can't use a digital controller. You need to have a population of neurons, and each neuron will respond with a different time scales. In an octopus, for example, the neurons here will react way faster than the neurons here, right? So you need different time scales, and this is what neuromorphic can give you. So in our opinion, this is a good way to start a benchmark and benchmarking for neuromorphic. Also because we got a little bit bored and tired with Neurobench. It's completely disembodied. It does not take into consideration the fact that a body needs to interact with a real scenario, okay? So we are a little bit sick and tired of simulated data. The world is not simulated. Try to any pipeline, any that gives you 97% accuracy there, and you will see it's not working. I promise you, it's not working. So we need to work there, not in the lab. We need to do it directly there, okay? So we gave different metrics and different tasks for the benchmark. This is one of the last works that I want to show you. It has been done together with the ETH. It's a completely analog, and what it does is the robot is trying to follow an artist painting, okay? It's completely on dynapse. So the vision part, the trajectory recognition, plus how much needs the force to be applied to not ruin the canvas and so on and so forth. Everything is run on the dynapse. Fun fact, we were at the exhibition, and if you could hear some fans, it was us with lots of fans on the dynapses, because of course the more the heat, the more the mismatch. So that was funny. Now, finished. The point is, I do lots of very lightweight models because in the future, my dream would be to try to go back to biomedical engineering, so trying to have some cortical or subretinal vision restoration prosthesis, right? So I want to go there at some point. So these are all of the beautiful people that I collaborate with. Yeah, these are my podcasts, Neuropack and Open Neuromorphic. Of course, more than happy if you wanna work with me. I wanted to show you also another thing I will tell you later. And these are my beautiful guys. And thank you so much for listening to me.